Indeed, we are counting points of circles. X squared plus y squared equals 2a. Okay. Chapter 1 over z. Okay. So the driving question we have is we want to know the number of solutions to x squared plus y squared equals n, where this number I will denote by number 2 because we're in 2 dimensions, and n. Okay, so this symbol denotes the number of solutions to x squared plus y squared equals to n. This, of course, is a geometric problem, right? We are trying to count the number of integral points, in other words, integer lattice points, with a distance of root n from 0, right? This is obviously a geometric problem, but the, I think, miraculous insight is that actually this is better solved as an algebraic problem. Okay, so what is the algebraic problem? It is the observation that x squared plus y squared can be factored, right? This is a factorization problem. X plus iy times x minus iy equals to n. In other words, as I said, a factorization problem in Z adjoin I, which is, I'll just define set theoretically as this. Okay. Where length, which was the geometry we had above, gives us this multiplicative map from Z mod I, oops, not Z mod I, Z adjoin I to Z, where this multiplicative map is an algebraic property, okay, and it's a very rich algebraic property that we will exploit in chapter 2. Okay. Now, because it is a factoring problem, it turns out that it suffices to understand this quantity, the number of points, for n is equal to a prime, because if you can just multiply things to get a prime, you can just multiply those things more to get n, right? So suffices to solve for n equals to a prime p. This is not to say that this going from a prime to a general integer n is not interesting. In fact, it's very beautiful. I recommend watching the 3 blue 1 brown video, pi hiding in prime regularities, for discussion of this. Okay, it's one of the most beautiful videos he has. And once one starts down this road, then one heads towards a lot of algebraic and analytic number theory too. So Dirichlet's class number formula, yada, yada. Okay, but that is beyond the scope of what I want to talk about. It is very beautiful, so I recommend you check it out. But today I will be just talking about solving it for primes. Okay. Let us first do an impossibility result. Okay. And the key observation here is, let's think about what values we cannot get with a single square. Okay, so what values not attained as a square? Okay. So recall from perhaps one of the first proofs you learned, in fact, one of the earliest proofs in math history, that the square root of 2 is irrational. Okay. What does this use? It uses that p squared equals 2q squared implies that actually p must be even. And so p squared is actually equal to 4 times some other number. Okay. In other words, this is saying that if an even number is a square, then it must be a multiple of 4. Okay. In other words, the only things mod 4, the only even number mod 4 that can be attained as a square is 0. Okay. So 0 mod 4, that is possible, and 2 mod 4 is impossible. Okay. So in other words, half of all even natural numbers cannot possibly be produced by squaring, at the very least, right? There's a lot more that cannot be produced, but at the very least, we know that more than half of them cannot be. Okay. And similarly, okay, half of all odd numbers cannot possibly be produced by squaring either, right? 2k plus 1 squared, 4k squared, 4k plus 1. This is 1 mod 4. So things that are 3 mod 4 cannot possibly be produced by squaring. Okay. And so therefore, a sum of 2 squares, well, the only things that one square can do is 0 mod 4 or 1 mod 4. And therefore, we can only get 0, 1, or 2 mod 4 as a sum of 2 squares. So what we have proven is that any number n, 4k plus 3, has no solutions. Okay. Very straightforward. Now, this is already foreshadowing that we will also be tackling the problem of answering how many solutions there are over other rings. Okay, for example, Z mod NZ. Okay, maybe I'll call it M because I already used up N here. Okay, so that will come later in chapter 2. Since today we'll have a lot of different mathematical fields, maybe I would just like to mention that, in a sense, Z is the hardest ring to solve these kind of questions in. Because Z admits a ring homomorphism to any other ring, right? Z is the initial object in the category of rings. And so if you can solve it in Z, then you can actually solve it in a bunch of other rings. Okay. In particular, what we used above is that if we have a solution in Z, then we can send that to a solution in Z mod 4. And we just showed in Z mod 4 that certain things can have no solutions. Okay. So that was the category theoretic insight of the day. What about P is equal to 4k plus 1, right? Most primes are either 4k plus 3 or 4k plus 1. There's only one that isn't, P equals 2. I might say a few words about P equals 2 throughout the hour, but I think most of the time that is just 4k plus 1 and 4k plus 3. Okay. This is a famous possibility result called Fermat's two-square theorem, also known as Fermat's Christmas theorem, because apparently he wrote it in a letter to somebody on Christmas Day in the 1600s, okay, some year in the 1600s. And there's a beautiful proof for this, okay. I learned this first from a video from Mathologer, okay. It's the windmill proof. It's just absolutely beautiful, okay. And the key insight is we are assuming that P is equal to 1 plus 4k, right? And we want to show that P is equal to x squared plus y squared, say. Okay. So let's consider a wider class of solutions that contains both these equations. Okay. So let's consider solutions to P is equal to x squared plus 4 yz. Okay. So clearly this encompasses P equals to 1 plus 4k and also encompasses P is equal to x squared plus y squared. Okay. Now, we will illustrate this equality in a number of ways. Okay, so here's some more geometry. I can illustrate it. Let me do an example. Example, 37 is equal to 3 squared plus 4 times 7 times 1. I hope that's true. Okay, I can illustrate this in one of two ways. I first draw my square. Okay. Give me some space. Okay. And I will pinpoint this upper left corner to be of note. Okay. What I can do is I can draw four stacks of four, columns. Okay, and I can attach these to this base square in two different ways. I can attach it like this. Okay, and then I can continue around the square as follows. Okay, or instead of attaching them horizontally on the red base point, I can attach them vertically. Okay, and then I will continue symmetrically around the base square. Okay, and so this gives me two different windmill shapes. Okay, the left one has a fatter base, right? There's a sort of 5 by 5 square going on here, whereas the right one has a skinnier base. Okay. Now, yeah. So in general, if I have an x by x square and a red base point here and a y by z rectangle, I can attach this red point to the base point of the square, either horizontally, okay, this is the horizontal configuration, or vertically, to get two different ways. Okay. Let's see. Two different ways of attaching. If and only if this thing is not a square, right? If it was actually a square, then the horizontal and vertical configuration would be the same. And so it would not produce a different picture, a different windmill shape. Okay. If it is a square, then there's only one way to attach. Notice that 2 is even and 1 is odd. Okay. So the key behind this proof is actually parity. For those of you who were around for my GSO talk on the Jordan curve theorem, in which I proved Sperner's lemma, that was another beautiful proof also based on parity. Okay. Okay. So we have an involution, or maybe if you prefer the word pairing. Okay. So these two come in a pair. Okay. And the fixed point of this involution, or the self pair, is precisely producing me y equals z, right? A square. That's p is equal to x squared plus 4y squared, which is what I'm looking for, right? So the self-pairing, or the fixed point of this involution or pairing, is precisely my goal. Okay, this is good news. It turns out that there is another involution, okay, another pairing. And that is comparing two windmill shapes of the same footprint. Okay, so let me draw you a picture. I can have a windmill shape that looks like this. Okay, or I can produce that same thing, and this is done with a horizontal configuration. Okay, I can produce that in the same way, the same shape, by doing this. Okay, so if you just look at the red bit, I get a fatter base, and now these extra tidbits are now vertical oriented. Okay, so a horizontal configuration with a small base corresponds with a vertical with a larger base. Okay, and these have the same footprint. So that's another pairing. Okay. All windmills, all such windmills, can be paired like this. except what? Except if I have a one by one base on the right-hand vertical side, right? Because in order to go to the left, I have to reduce the size of the base. Okay, so if I had a one by one base, in other words, if I started with a vertical configuration like this, there's no way for me to associate with that a horizontal configuration. Okay, and so this is the self-pairing over here. But what is this? This is p is equal to 1 plus 4 times k times 1. Okay, so the two sort of endpoints, okay, are appearing as fixed points of my pairings. Okay. Now the insight, the final blow is down here. I am sure that I have some pairs plus one exception. Okay, exactly one exception for an odd number of windmills total. And so going back up here, right? I have an even number coming from cases where y does not equal to z, and an odd number coming from cases where y does equal to z. And so if the total number of windmills is odd, then in fact, there must be at least one of these ways to attach. Okay. Okay. In other words, there must be at least one case where y does equal z. And so I have proven that there exists x and y, so that p is equal to x squared plus 4y squared. Questions about this proof? Comments? Okay, no comments. I will say that you can watch Mathologer do it. He has nice animations. Okay. Maybe you will think that he makes more sense than me. But either way, it is a beautiful proof. And I hope you also find it to be beautiful. Okay. So now what? That is the end of chapter 1. We have figured out well, we haven't so much as counted, but we have done a large amount of work, and you can finish the count as 3 blue 1 brown does. Okay, but what I want to do is I want to move on to chapter 2, where we actually will give a precise count. Okay, precise count is now the question I alluded to before, solving x squared plus y squared equals a in z mod nz. Okay, which I will think of as 0 all the way up to n minus 1 as a set. Okay, and the number here will be denoted number sub n, because we are over z mod nz, evaluated at a. Okay. All right. Geometric visualization. We can think of this as x squared plus y squared equals a, or a plus n, or a plus 2n, all the way down. Okay, so we have concentric circles. And let me call this collection curly C sub A. Okay, so curly C sub A will be all of these circles that course where integer points on these circles correspond with solutions in z mod nz to x squared plus y squared equals to a. Okay. I will see if I have some pictures. Okay, so for example, for n is equal to 12, okay, I have plotted in light gray all of the circles. So all of the gray points here are forming the collection curly C sub A equals to 0. And the red points are integer points on the circles. Okay. And I have a bunch of examples here. Okay. Now, I would like to make some algebraic observations. First, the trivial one. If I have an n by n box, one side is open, the other closed. No matter where I shift it on this plane, it will contain the same number of points. Okay, and I claim this is a trivial algebraic observation. First of all, let us observe that indeed, if we draw any 12 by 12 box, and I shift this box anywhere, okay, it will have the same number of points. In the example boxes that I have already drawn, okay, this is true. But why is it true in general? Well, it's very trivial, okay. It comes from the observation that if x squared plus y squared equals to a mod n, then x plus kn squared plus, no, sorry, let's call it alpha n squared plus y plus beta n squared is equal to a mod n as well, right? So absolutely trivial. Okay. But this tells us that all solutions occur periodically. Okay. In other words, if this is a solution, okay, an integer point on the circles, then so is this one, and then so is this one, and then so is this one, and so forth. Okay. I think this is highly non-obvious from a geometric perspective, right? The circles are, very centered around 0, but we have this assurance just from trivial algebra that no matter where we shift the box, even though the circles get denser and denser further away, there will be the same number of integer points. Okay, I think this is very unintuitive, at least from a geometric perspective. Okay, so no matter where you shift the box, same number of solutions. Okay. Now, a less trivial algebraic observation. Recall now the multiplicative norm map before, okay, that I called the length. Okay. So this maps x plus iy maps to x squared plus y squared. Okay, and here it's done mod n, whatever. This is the multiplicative map from before. Okay, I can restrict to now the group of units. Okay, so instead of everybody, I just want to restrict to those who have an inverse, a multiplicative inverse. Okay, so that's denoted z mod nzi star or cross. Okay, and that will map also to the group of units. Okay, and now this becomes a group homomorphism. Okay, so now recall from maybe week 1 of an algebra class, if I have a surjective group homomorphism, GH, then all fibers are of the same size. Okay, and this comes from another easy lemma. The fibers are all of the form G times the kernel of phi. Okay. I will not prove it for you. I will assume that most of us here have indeed taken at least 1 week of an algebra class. Okay. But what does this tell us? This tells us that actually x squared plus y squared equals to a. For many different a, indeed for all a in z mod nz cross, there's the same number of solutions. Okay. So in other words, this count is very regular over different choices of radii. Okay. So you have 2 freedoms. We can move the box around, and that will keep the solutions the same. And I can sort of ripple the circles out. Okay. And this is especially, important for n is equal to a prime. Because in that case, z mod pz star is in fact most of z mod pz. Okay, it's just 1 through p minus 1. So the only thing that is not a unit in z mod pz is 0. In other words, z mod pz is a field. Okay. So in fact, all but one of these counts are steady. Okay. Questions so far? Comments? There's something in the chat. Never mind, it is not relevant. All right. So I think this is an amazing geometric regularity. Just astounding, to be honest. It follows from very basic algebra, but just from looking at the pictures, it would have been beyond my wildest dream that these things are true. So I've illustrated in this case for n equals to 12, which you should recall is not prime. But I chose a equals to 1 and a equals to 5, which are relatively prime to 12, and hence in the group of units. And you can count that in all of these boxes, there are indeed 32 integer lattice points. Okay. The numbers are different for different choices of a that do not happen to be relatively prime. For example, a equals 3, there are in fact no points. For a equals to 0, there are few, 4 of them. Okay. And then for, let's see, for n equals to 13, okay, there are these are the pictures for that. Okay. Just so you get some sort of visuals. Okay, I promised visuals, so I'm delivering. All right. Okay. Summary. We have some collections of circles, curly C sub A. Okay, for A is equal to 0 to p minus 1 for a total of p. Okay, p collections of circles. And they cover completely all lattice points in 0 to p minus 1 squared. Okay, or in fact, in any box. But in this specific box, the canonical standard box, there are a total of p squared points. Okay, so on average, okay, for a uniform choice of A, okay, A taken uniformly in p minus 1, okay, here's our probability of the evening. Each CA contains p lattice points in any, I'll just say in this box, okay? And I will write that as EA, sorry, the number of solutions in dimension 2 over z mod pz of x squared plus y squared equals to A on average is equal to p. Okay. Simple equation. Okay. And in fact, using the group homomorphism above, we got that all collections but one, in other words, all collections being A is equal to C1 through CP minus 1, and the one exception is C0. That's the only number which is not in Z mod PZ star. Okay. All of them but one have the same count. Okay. This is enough to actually tell us a lot of information. Okay. So let me sketch for you roughly what the possibilities are. Okay. So the y-axis here is the count. Okay. In 2 dimensions, this, also known as the size of these collections of circles inside the box. Okay. So what could happen is that 0 is anomalously big. Okay, so there are many more points in 0, and everybody else has to decrease from the average p to compensate. Okay, so that's one possibility. The other possibility is 0 has very few. Okay, and so everybody else has to rise a little bit from the average p to compensate. And of course, the last possibility is that, in fact, there's just p everywhere. Okay, so these are the three possibilities. And now it turns out that basically I can solve the entire problem. Okay, so three observations. First, before I observe, let me define. So say that this count takes the value capital Z at 0, in other words, at a equals 0. Okay, and it takes the value a at all other values. Okay, so a is equal to 1 through p minus 1. All right, well, first observation, Z plus a times p minus 1 has got to equal the total number of points in the box, which is p squared. Or in other words, Z minus a has to be 0 mod p. Okay, so there's this sort of quantization going on. Okay, the difference can't just be anything. It has to be a multiple of p. It either has to be perfectly flat, or if there's a jump, it's going to jump a lot. Okay. The second observation is a very rough bound coming just from algebra. The value of z must be bounded between 0 and 2 times p. Why is this true? Well, it's true because z counts the solutions to p many quadratic equations, right? X squared plus 0 equals 0, x squared plus 1 equals 0, all the way down to x squared plus p minus 1 squared equals to 0. All of that is mod p, of course, over the field fp. Okay. And a quadratic equation over a field has at most two solutions. Okay. And if there's p many quadratic equations, then that's a total of at most 2p many solutions. Okay. All right. This tells, okay, 1 and 2 put together tell us that, in fact, z can only be 1, p, or 2p minus 1. Okay, those are the only possibilities. The third observation is to, let's figure out when does z equals 1 happen. Okay, so z equals 1 happen, z equals to 1 happens if and only if the only solution to x squared plus y squared equals to 0, in other words, x squared equals minus y squared mod p, is 0, 0. Okay, that's the only solution. Now, when can that happen? Let's suppose the opposite. Let's suppose that there exists y in z mod pzx and exists x depending on y such that x squared equals minus y squared mod p. Okay. Well, my claim is that simply by multiplying or dividing, let's say, divide by y squared, because y is in the unit group, right? It has an inverse. I get z over y, sorry, not z, x over y squared is equal to minus 1 mod p. Okay. So there exists another solution, x comma y, implies, in fact, there exists a solution where y equals to 1. For y equals to 1, exists x in z pz, such that x squared is equal to negative 1 mod p. Okay. And in fact, this is strong enough to imply that for all y exists x such that x squared equals to minus y squared mod p. Because once I have negative 1, I could just multiply that particular x by the new y, and then I can solve a general thing. Okay, so actually we get a very interesting phenomenon. We get a quantifier boost, right? So initially we started by assuming there exists only one solution. Okay, and by going around in the circle, we actually get that there exists a lot more solutions. And this is exactly the same phenomenon that we saw above, right? And we saw previously that there's a quantification going on, quantization going on, where if it's not zero, it has to jump all the way up to a multiple of p. Okay. Now, let me continue. This is if and only if there exists an element of order 4 in Z mod PZ star. Okay. Yes, there's a caveat that we're assuming P is not equal to 2 here. So if P is not equal to 2, then -1 is actually different from 1. And so x squared equals to -1 means there is an element of order 4. Okay. In other words, I mean, that is x is order 4. Okay. But this, recall, is isomorphic to Z mod P minus 1. Okay. And which is a cyclic group. And we know exactly what elements of order blank are in cyclic groups. This is if and only if P is equal to 4k plus 1. Okay. So we have figured out that Z equals 1 happens if and only if P is equal to 4k plus 1. Okay. And then Z equals to 2p minus 1. The other extreme happens when P is equal to 4k plus 3. Okay. And in fact, the last option does actually happen when P is equal to 2. Okay, so let me just summarize that. So this is for P is equal to 4k plus 1. This value, wait a minute. Sorry, my bad. I misspoke. This is the opposite, okay? The opposite. So this was supposing that Z is not equal to 1. Okay. So Z is equal to 2p minus 1 if and only if P is equal to 4k plus 1. Okay. So this is 2p minus 1. And everybody else, therefore, has to be P minus 1. Okay. And for P equals 4k plus 3, at 0, I get 1. And everywhere else, I get P plus 1. And then for P equals to 2, you can just check this because P equals 2 is very easy to check. Indeed, everyone is flat. Okay. Questions, comments before I continue onward? Okay. Allow me to make some illustrations, okay, to just show you visually what's going on. Okay, so first I will draw the picture for P equals to 13. This is the picture for P equals 19. 13 is, of course, 4k plus 1, and 19 is a 4k plus 3 prime. Okay, what do we observe? Here I've plotted out, this is the number of solutions in dimension 1 over P of A. Okay, so what I've done is I've just listed out all possible squares, mod 13. Okay, so 0 is going to be 0 squared. 1 is going to be 1 squared, but also 12 squared, right? And then 3 is going to be 4 squared, mod 13, and so forth. So I've just filled it out. 0 has 1 solution, and everybody else has 2 solutions. Okay. And what do we observe? We observe that it's symmetrical over this reflection point, right? Flipping over 6 and 7, it precisely matches because of the thing I just proved. Wait, right. Flipping over is negation, and I just proved that for 4k plus 1, there are indeed solutions to x squared equals to negative y squared mod p. Okay. Whereas if we look at p equals to 4k plus 3, and I draw the separating middle line between 9 and 10, then we see that it perfectly cancels. Like it perfectly misses. So over here, we had a perfect coincidence. Everything over here is symmetrical over here. But over here, everything here, it's reflected to a gap on the other side. And this is reflecting the fact that in 4k plus 3, we do not have solutions to x squared equals to negative y squared. Okay. This gap corresponds to this hole. And so if I fold it, all the bars, slot into the gaps on the other side. Okay. So that's just a picture of what's going on. It's a very visual phenomenon. Okay. And then I must make some more interludes before we make our final descent into quadratic reciprocity. Okay. So proposition for p not equal to 2, as always, z pz 2 is, in other words, all of the squares. Okay, this is the set of a squared for a and z mod pz star forms a subgroup of z pz star. And the squaring mapping from this to the square subgroup is a group homomorphism of fiber size 2. Right? I told you before that group homomorphisms have the same fiber, and in this case, the fiber size is 2. Okay. It is important. Okay, so please bear with me. This implies that the size of the square subgroup is precisely half that of z mod pz star, which remember is isomorphic to the cyclic group z mod p minus 1. And so the size is precisely p minus 1 over 2. Okay. For those of you who know any quadratic reciprocity, bells should start ringing when you see p minus 1 over 2. Okay. Lagrange's theorem tells us that squares therefore will satisfy the polynomial equation x to the p minus 1 over 2 is congruent to 1 mod p, right? This is the order of the group, and any element raised to the order of the group has got to be 1, the identity. Okay. But in a field such as Fp, the number of solutions to this type of equation is bounded by the degree. Okay. But I have already found for you precisely p minus 1 over 2 solutions to this thing. Okay, it's all the squares. And so this tells us that indeed all non-squares are not solutions to this thing. But because they have to be solutions of x to the p minus 1 is congruent to 1 mod p, by Lagrange's theorem applied to the bigger group, it must be that all non-squares satisfy x to the p minus 1 over 2 is congruent to negative 1 mod p. Okay. So in fact, we have discovered just by raising an element to the p minus 1 over 2 power a dichotomy. Okay, precisely matching the square versus non-square dichotomy. Okay, and this I will summarize as Euler's criterion. Okay, that's the name of this fact. X to the p minus 1 over 2 is congruent to this symbol, which I will define momentarily. This is called the Lagrange symbol. It is defined to be 1 if x is a square mod p, 0 if x is equal to 0, and negative 1 if x is a non-square. Okay, we have just proven this result. If x is a square, then indeed raised to the p minus 1 over 2 power, it's 1. If it's not a square, then it cannot be 1 because there are only bounded number of solutions to that. So it must be the other option, which is negative 1. And we have thus produced Euler's criterion. Okay. We are now finally ready to go to higher dimensions. Okay. So chapter 3, higher dimensions. Okay. Why might one think about doing this? It is because for dimension 2, we already saw that there's a remarkable stability of solutions as the circles ripple outward, right? But what is the picture of a three-dimensional sphere passing through two-dimensional plane, right? It's a circle rippling outward. In other words, a sphere is composed of just slices of circles, and we have a very good understanding of counts of these slices. So it is not a far stretch to imagine that we can easily use those numbers to count the number of solutions to at least a three-dimensional sphere, right? We might not be able to go higher, but at least for spheres, we understand the situation well enough that we can just add all of those slices together to produce an answer. Okay. So by the way, the picture of a 3D sphere passing through a 2D plane and producing ripples of circles is beautifully illustrated in there are these online animations of a famous mathematical novel, Flatland. Okay, I think it's just fantastic book and movie. Okay, there's like an animated movie just online on YouTube for free. Um, um, I really recommend it. But in there, a major plot point is a three-dimensional sphere passes through a two-dimensional plane, and all the two-dimensional people on the plane freak out. Okay, so just cool thing to check out. All right, higher dimensions. We know this count, the two-dimensional count, over Z mod PZA completely. And we also know the count in one dimension. Okay. This is just 1 plus the Legendre symbol A in Z mod P, because we get one extra solution. Hold on, where was it? Here. Normally, for 0, it's one solution. And if it's a square, I get 2. And if it's not a square, I get 0. Okay. And so 1 at 0, 2 at a square, 0 at not a square is precisely 1 plus the Legendre symbol, right? The Legendre symbol, remember, was 1 at a square, 0 at 0, and -1 at a non-square. Okay. So we know the two-dimensional and the one-dimensional things, so it is not surprising that we can put it together to get a three-dimensional. Okay, but actually, here is where the analysis kicks in. Just absolutely beautiful. Observe that in d dimensions, okay, x1 squared plus all the way up to d dimensions, to a naught, okay, I can try to sum or try to understand this by holding fixed the value of two of these, right? In other words, every solution of this d-dimensional equation can be broken down into a solution of the two-dimensional equation and a solution of the d minus two-dimensional equation. Okay. In other words, if x1 squared plus x2 squared is equal to a, then I'm looking to solve the x3 upward equals to a0 minus a. Okay. And if you're an analyst, your spidey senses should be tingling because this describes a convolution. Okay. Maybe they were tingling a long time ago, but please bear with me. So the d-dimensional count is actually a convolution of the two-dimensional count. And I'm choosing 2 because 2 is particularly regular, right? We know the count for 2 dimensions, and we know that it's mostly flat. And this is key. Okay. It's going to be the convolution of the d minus two-dimensional count with the two-dimensional count. Okay. So in other words, the count is equal to this. Okay. Great. Convolution. We're almost done. Almost done. One last proposition, and this is a proposition of analysis. Maybe probability theory, if you want to look at it that way. Okay. If f and g have mean, okay, they're integral, we are over a measure one, sorry, yeah. The measure space is this, okay? The total mass is 1. They have mean mu f and mu g respectively. Then f minus mu f convolve g minus mu g is equal to what? It's equal to f convolve g minus mu f convolve g minus mu g convolve f minus, sorry, plus mu f convolve mu g. Okay, what is this in turn? Well, this is just mu f, right? Remember the convolution is an integral. I pull the integral outside because this is a constant. I get this, which is mu f times mu g. Similarly, this is equal to mu f times mu g, and this is also equal to mu f times mu g. I get minus 2 mu f mu g plus 1 mu f mu g, and so in total I get f star g minus mu f times mu g. Okay, and more generally, I can shift by any constant. Okay, more generally, observe that constant convolve f minus mu f is equal to 0. Again, because if you just expand out the convolution, you'll get two numbers that cancel each other. Okay, and so what can we do? We have this is a convolution, and this is telling us that I can shift one of them by any constant. Okay, so let me just finish my chain of thought. F minus mu f convolve g minus any constant is still equal to f convolve g minus mu f times mu g, where this is also equal to the expectation or expected value of this. Okay, so what have I done? In particular, I have said that the d-dimensional count over P minus the average of the d-dimensional count, which is a simple number, I'll get to it in a moment, is equal to the d minus 2-dimensional count minus its mean times this dude, where I can now subtract any constant. Okay, sorry, this is a convolution. I can subtract any constant. And what constant do I choose? I obviously choose the constant that makes most of it 0. Okay, to remind you, what does the number of solutions in 2 dimensions look like? It's precisely this. Okay, so let me go back down. This is the number of solutions in 2 dimensions. And what I can do is I can just shift everybody so that now 0 is aligned with most of them. Okay, so 0 is aligned with most of them. Then what happens? So any constant. Okay, so let me, sorry for more notation, let me call this epsilon dp. Okay. Okay, that is the deviation from the mean. What is the mean? Well, in d dimensions, okay, maybe I'll ask you, what is the mean? What is the mean? Well, in d dimensions, I have a box 0 by p minus 1 to the d box. Okay, and I still only have p circles or p spheres. Okay, or in other words, p choices of A0. So the mean is just p to the d over p, or in other words, p to the d minus 1. Okay. Okay. We're almost there. What I have shown is that the deviation from the mean at a0 is equal to the deviation in d minus 2 dimensions convolved with -1 to the p minus 1 over 2 times p times delta of 0, where this is the result of subtracting the appropriate constant from the two-dimensional count, so that now most of them are 0. For instance, for p equals to k plus 1, when I subtract by p minus 1, everybody else gets shifted downward to 0, and what's left is a height p block. Okay. Similarly, if I shift all of these guys downward by 1 unit, then this guy is, not down. If I shift all of these so that these guys are at 0, then this is now at negative p. Okay, it's p units down. Okay, and so that's where this comes from. For p equals to 4k plus 1, it's p units up at 0. For p equals to 4k plus 3, it's p units down. Okay, and that's where the formula comes from. All right. We are in the home stretch. What is the convolution of the delta function with this? Sorry, at a0. Okay. Well, it is just applying this function at a0, right? Convolution with the delta function. This is therefore just -1 to the p minus 1 over 2 times p times the deviation in d minus 2 dimensions at a0. So we have a very beautiful recursive formula telling us a relationship between the deviations in d dimensions with the deviation in d minus 2 dimensions. And now, of course, we can iterate. Okay. So by iteration, we arrive at this. The total count is the mean, okay, p to the d minus 1, plus this deviation term, which, when iterated, produces this. Why? Because I can just keep iterating this downward until I get down to this. Okay. How many steps do I need to iterate? Well, I need to, each time I go down by 2, right? And so if I start at d, in order to get down to 1, I go down by d minus 1 over 2 steps. Okay. Then I'm left with this, but this was just the Legendre symbol, okay, because of this. Okay, so this is the mean in one dimension, and this is the deviation. Deviation. Okay. Combining everything together, what do we have? Sorry, I'm going over time. There's one where the plane is landing. Okay, the plane is landing. The final observation is as follows. Spheres have a property where I can rotate them, and they are still invariant. Okay, so if I count the number of points on a sphere, I can rotate it, and it must still be the same count. In other words, what am I doing? I'm considering the action of z mod dz on solutions x1 through xd of 0 to p minus 1 to the d, x1 squared plus xd squared equals to 1, let's say. Okay. Now, you may recall also from maybe week 2 of an algebra course that there is a very useful theorem. In fact, this one can be used to prove all the Celoff theorems. Okay, this is the P group fixed point theorem. Okay. I don't think I will explain it completely in generality here, but what the point is, if D is a prime, then the possible orbits have a very restrictive size, right? What are the possible orbits as I apply this action? They must form a sort of cycle, right? And a cycle must divide the total, length of the largest possible cycle. And if D is a prime P, or actually let me call it Q because I've already used up P, then in fact the orbits must either be singletons, in other words, it's a fixed point, or it's a complete orbit. Okay. So if D is equal to a prime Q, not equal to P, then the orbits of this action are either a single point, in other words, a fixed point, or come in a collection size Q. Okay. And X is a fixed point if what? If all of these are the same number. Okay, so in other words, there's a fixed point if and only if I have Q times X squared is equal to 1 mod P, i.e. Q is equal to X inverse squared mod P, or in other words, Q is a square mod P, or in other words, Q Lagrange symbol P is plus 1. Okay. And finally, taking everybody mod Q, taking this entire equation mod Q, I arrive at the number of solutions here. Okay, so the number of fixed points, which from this is precisely the number is precisely 1 plus QP equals to P to the Q minus 1 mod Q plus minus 1 to the P minus 1 over 2 Q minus 1 over 2 times 1 Lagrange symbol P mod Q. All right, what is this? This is equal to 1. Okay, what is this? Is 1 a square mod P? Oh, why, yes, of course it is. Okay. So what do we have? We have 1 plus QP is equal to 1 plus this expression. Okay. Times, sorry, I missed a term. This also has to show up there. Okay, I forgot that guy. Times P to the D minus 1 over 2 mod Q. But this is exactly what was covered when I talked about Euler's criterion. Okay, and this is precisely equal to P Lagrange symbol Q. And so what have we proven? We have proven the law of quadratic reciprocity, just by counting points. Okay. QED. That's it. It's over.